Hello friends, in last video lecture we have learned about the intrinsic and extrinsic semiconductor. In extrinsic semiconductor there are exactly two types, p-type semiconductor and n-type semiconductor. Now today we will learn about the p-n junction diode. p-n junction diode. The name suggests the p-n junction diode. p-n junction diode. In p-n junction diode, P represent the p-type semiconductor and N represent the n-type semiconductor. In n-type semiconductor, the majority charge carriers are electrons, and in p-type semiconductor, majority charge carriers are holes. In n-type semiconductor, minorities are holes. In p-type semiconductor, minorities are electrons. Now, in n-type semiconductor, we have added the pentavalent impurities, while in p-type semiconductor, we have added the trivalent impurities. Pentavalent impurities like arsenic and trivalent impurity like aluminum. In pentavalent impurity, in arsenic atom, in outer orbit having 5 valence electron, 4 valence electron out of 5 to take apart to form a covalent bond with neighboring atom, with neighboring silicon atom, and 1 electron gets by the crystal. While in p-type semiconductor, trivalent impurities like aluminum, in outer orbit of the aluminum atom having 3 valence electron, only 3 valence electron, and fourth place the deficiency of the electron means, at fourth place deficiency of the electrons means holes, which attract the electrons from the another atom, which electrons free from the covalent bond. Whenever we increasing the temperature, covalent bond breaks and electron becomes free. That electrons can be attracted by that hole. Now, p-n junction diode. In p-n junction diode, p-type and n-type. First of all, we have take p-type wafer and n-type wafer. P section and N section. When we join P section and N section, one boundary is created between P type and N type. When we join P section and N section, P type semiconductor and N type semiconductor, one boundary is created. That boundary is known as the junction. p-n junction diode. We know that in p-type semiconductor, trivalent impurities like aluminum. In p-type semiconductor, majorities are holes. Represented by the circle. And in p-type semiconductor, minorities are electron, represented by dot. Now in n-type semiconductor, majorities are electron, because of pentavalent impurities. When we added pentavalent impurity having 5 valence electron, 4 valence electron to take apart to form a covalent bond, and 1 extra electron donates the crystal. Pentavalent impurity, 1 electron donates to the crystal. And minorities are holes in n-type semiconductor. Minorities are holes. Now we will see here near the boundary of the n side, electron near the boundary of p side, holes. We know that holes having charge negative, and electron having charge negative and holes behaves as a positive particle, which is not a positive particle, which is not a real particle. Only we imagine that holes behave as a positive particle. Now, when we join P section and N section near the boundary, one side majorities are electron and other side majorities are holes. Now, the one process is started. When we joined P section and N section, one process is start, and that process is known as the diffusion process. Process is diffusion process. Diffusion process means the ability of electron to move towards the positive ion. The ability of the electron to move towards the positive ion, and the ability of the holes to move towards the negative ion. Electrons near the boundary, near the junction, moves toward the N section to the P section. Electron moves from N section to the P section. And diffuses itself. When electron moves from N section to the P section, electron moves from N section to the P section. At that time, we know that when electrons, movement of the electron, because of movement of the electron, some current is flows. That current is momentary current. Here, that current is momentary current, or we can say little bit current. Because of diffusion process, from N to P, electrons moves from N to P, N to P, N to P. Diffusion process, because of the diffusion process, the diffusion current, that current is momentary current, little bit current, and we can say that current is diffusion current because of process of diffusion, current is flows, and that current is known as the diffusion current. Why diffusion current? Because movement of the electron, little bit current is flows. When electron moves from N to P, little bit current flows. That current is diffusion current. Diffusion current. Only little bit current flows. Now, when the process is started, diffusion, after that, when one layer is created between P-type and N-type semiconductor, one layer is created. After the diffusion process, one layer is created. We know that here electron near the boundary moves from N section to the P section. When any object loses the electron, that object becomes positive. When any object gains the electron, then object becomes negative. Now, in N section, electron moves from N section to the P section, N section to the P section. Therefore, near the boundary, here electron moves. When the electron moves, electron release the object, it becomes positive. Here plus plus plus. When any object gains the electron, here p-type semiconductor gains the electron, it becomes negative near the boundary. Now, because of positive 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 and because of negative negative negative, here electric field set up inside the device. Electric field set up inside the device. The direction of electric field, the direction of electric field from positive to negative, always from higher potential to the lower potential. Now, one layer is created between p-type semiconductor and n-type semiconductor. That layer is depletion layer. One layer is created. That layer is represented by the depletion layer. Because why depletion layer? Because here electron, the absence of the electron, absence of the immobile ion, we can say in that region is in depletion layer. In depletion layer, all the ions are immobile. All the ions are immobile. All the ions are in bound condition in that region, and because of that electrons, the current do not flows from that section. Now, electric field, the role of electric field, we know that it offers the electrons to move from one level to the next level. But here the role of the electric field, which do not support the electrons. Here electric field do not support the electron. Here to constitute a electrical current. Here electric field opposes. Here electric field opposes to the electrons to constitute a electric current. Why opposes? Because the direction of the electric field from positive to negative. The direction of the electric field from positive to negative. And when we connect the battery, the conventional current flows from plus, P with plus and N with minus in this direction, in opposite direction. Because of the opposite direction, here electric field opposes to the electrons to flow the conventional current. Now, question arises in our mind. Electron near the boundary in n section. Electron near the boundary in n section moves from n to p. Why these electrons do not move from n section to the p section? Because at room temperature, little bit energy gets the electron, and electron moves from n section to the p section. Same as in p section, minority holes moves from p section to the n section and diffuses itself. Here movement of the electron because of the diffusion process, and electron diffuses itself in the p section's hole. Now, once a depletion layer set up in the device, that is permanent for the device. Once the depletion layer set up in the device, that is permanent for that device. Now, can we increase or decrease the width of the depletion layer? Can we increase or decrease the width of the depletion layer? Answer is yes. How? How can we increase or decrease the width of the depletion layer? we increase the concentration level in P section as well as in N section. When we increase the concentration level in P section and in N section. In P section, when we increase the concentration means here concentration of trivalent impurities, and in N section the concentration of the pentavalent impurities. When we increase the trivalent impurities in P section, the number of holes increases. When we increase the pentavalent impurities in N section, number of electron increases. We know that the majorities are electrons in N section and majorities are holes in P section. Because of majorities, holes behaves as a positive ion. Holes behaves as a positive ion. We know that positive repulsion, and here negative repulsion. Because of the repulsion, holes create a force in this direction. In same way in N section, negative electrons repulsion, electron create a force in this direction, and force from N section this side and force from P side this side, and shrink the depletion layer. In this way we can increase or decrease the width of the depletion layer. Again, in this way, when we increase the concentration level, we can increase the width of the depletion layer, and when we decrease the concentration level, we can decrease the width of the depletion layer. Now, here electric field set up in the device that is permanent. Now, which opposes the to flow a conventional current, to flow a current. Now, at higher potential, at lower potential. At higher potential and lower potential. Higher potential is represented by in this way, and lower potential is represented by in this way. And width of the depletion layer represented by in this manner. Width of the, that is the height of the depletion layer and the width of the depletion layer. Now, here width of the depletion layer approximately 0.5 micrometer. Width of the depletion layer. Width of the depletion layer approximately 0.5 micrometer. 0.5 micrometer plus and minus. Now, electric field at particular distance. Electric field at particular distance D. Electric field E into D. Electric field at particular distance which creates the potential difference V. V is equal to E into D. V is equal to E into D. Because of the electric field, here potential difference set up in the device. In electric field which opposes the charge carriers, Now, suppose here electric field set up in the device, that is 1 electron volt. Electric field set up in the device, that is 1 EV. And if we provide external voltage below that EV, suppose external voltage, when we provide external energy, external potential difference, that is 0.5 EV, then conventional current flow, answer is no. Why? Because here one obstacle is created. One obstacle is created here because of the electric field, because of the depletion layer. That's why that obstacle is known as the barrier. That obstacle is known as the barrier. That's why from that word we can say potential barrier. Potential barrier or depletion barrier. Depletion obstacle means barrier. One barrier is created. That barrier is potential barrier or depletion barrier. So we can say the height and width of the potential barrier or height and width of the depletion barrier, both are same. Now for silicon, that energy is 0.7, and for germanium energy is 0.3. Now if we provide exceed value of 0.7, then conventional current flow inside the device. If we use germanium crystal, then 0.3 volt. If we provide exceed value of 0.3, means higher value of the 0.3, then conventional current flows inside the device. If we provide below energy, that energy is below 0.3 volt, then current do not flow in the device. And for silicon, if we provide 0.7 volt, below this 0.7 volt energy, then conventional current do not flow in the device because of the one obstacle, one barrier created in the device. That barrier is one type of obstacle. Due to that we can say potential barrier or depletion barrier. Now symbol of PN junction diode. Symbol of PN junction diode. Symbol of PN junction diode. Arrow represent the negative, means N section, and here P section means positive. P section means positive and P section. Now the direction shows the flow of conventional current. Direction represent the flow of conventional current. That is one end from P, that is anode, and here cathode. Anode and cathode. Symbol of PN junction diode. Now in next topic we will use that symbol and we provide a external voltage, external potential voltage, potential difference to this PN junction diode. At that time what happens, that we will see in next video lecture. Today we have learned about the PN junction diode. In PN junction diode, 4 words important. First one is we will add one P type, one N types semiconductor. When we join P type and N type semiconductor, one boundary is created, that is junction and PN junction diode. After that, when we join the PN junction diode, that is diffusion process starts. Diffusion process starts. Second one. In third, when the diffusion process starts, the little bit momentary current is flows. That current is diffusion current. After that, when diffusion process stops, one layer is created, that is depletion layer. When any object or any body loses the electron, it becomes positive, and when any object or any body gains the electron, it becomes negative. Here plus plus plus, here minus minus minus. The direction of electric field, direction of electric field from positive to negative, from higher potential to the lower potential. Now electric field setup in the device, higher potential and lower potential. Because of the electric field at particular distance, potential difference V is equal to E into D. Now when we increase or decrease the concentration level in P type and in N type semiconductor, we can increase or decrease the width of the depletion layer. Depletion layer that opposes the charge carriers, which opposes the charge carriers. Because of opposes the charge carriers, it behaves like a barrier. Barrier means the potential barrier, or we can say the depletion barrier. That is the depletion barrier, and the width and the height of the potential barrier or depletion barrier. In next video lecture, we will see biasing of the PN junction diode. We provide an external battery. We will see the forward bias and reverse bias of PN junction diode. Thank you.